I know that's a long introduction. I just want to set the stage. I want to set the table. I want to set the Thanksgiving table. I want to set the Thanksgiving table with the turkey and the stuffing. I want the salad on there. I want the mushroom soup and the cranberry sauce. I want it all. Something like positive 4 times positive 3 means we want... What that means is we're actually going to take away 4 rows. I really should do this differently. No! I'm gonna fight! I'm gonna fight! That's not a song. Good morning, good afternoon, good evening, good whatever time it is where you are. Welcome to your Thursday Math Minute. I had a comment on the most recent video that said the Math Minute was not actually posted on the day in the video that I said it would be posted on. I can neither confirm nor deny that sometimes I record on one day and then post on another. The comment also said that the Math Minute, which as you know is guaranteed to be no more than 10 minutes, was actually 12 and a half minutes. And that feels like fake news. I mean, isn't time a relative concept anyway? Other things that I've been told to do lately. Shout out to my subscribers. I'm shouting you out. I hope that feels good. Subscribe, click the bell, get the notifications on, like, throw me that thumbs up. And if you do, you're a part of my, they gave themselves a name. You're my notifications crew? I don't know. But anyway, you are my crew and thank you for subscribing. We are coming back for part 2 today of this video on multiplication, the fundamental nature of multiplication. Is multiplication simply repeated addition, or is it something more? And I think you can already tell I come down on the it is something more side. So we want to figure out today a little bit more about what that could be. Specifically, we said, all right, yes, multiplication gives the same answer as repeated addition or skip counting. So I can look at something here like 5 times 7 equals 35, and I can say, okay, so again, let's read this literally as 5 times a 7, right? In other words, we're going to see a 7 5 times, and that's precisely what we see as we look across our rows, right? 1, 2, 5 rows of 7, which we said was another way to interpret this multiplication statement, 5 rows of 7. And again, we can skip count, 7, 14, 21, 28, 35. That gets us 35. Of course, the other thing that we can do is we could say, you know what? Because this is just an array, that's a fancy word for rectangle, there's no reason that we have to think of it as 5 times 7. We could just as easily, what am I trying to do here? We could just as easily think of it as 7 times 5. And so then we could skip count by 5s instead. 5, 10, 15, 20, 25, 30, 35. And either way we get 35 here. Of course, we did say this is literally a different multiplication statement. This would now be 7 times 5 equals 35, because I can see, oh, that would be 7 rows of 5, or 7 groups of 5, right? 1, 2, 3, 4, 7 groups of 5, 7 rows with 5 items each. So we know that multiplication will give the same answer as repeated addition when we're using the counting numbers, things like 7 and 5 and 10 and 100 and a billion. Oh, I guess I should say, so this actually has a name, right? The idea that I can take my array and I can change its dimensions simply by rotating, and I can see that a 5 by 7 rectangle and a 7 by 5 rectangle end up having the same area. We call that commutativity. Commutativity is what says 5 times 7 and 7 times 5 will be the same result. Multiplication as an operation has commutativity. We might think, oh, maybe that's one of the differences that makes multiplication something more than repeated addition, but unfortunately you may be familiar with addition and know that addition also has commutativity. 5 plus 6 is 11, 6 plus 5 also 11, right? The order in which you add two numbers makes no difference to the outcome. Both addition and multiplication are commutative. That's not going to be a big difference between the two of them, but that is the property that allows us to rotate this rectangle and see that its area is the same either way. So the product, the result of the multiplication, is the same either way. And we will use this. We'll come back to this idea in a second. But we want to take this and we want to start to understand what happens when we don't use the natural numbers. What if we use the integers instead? The integers are all the natural numbers, their opposites, and 0. And when we say opposites in this context, we mean opposites signed. So 5 and -5. 10, and negative 10. We want to be able to investigate multiplication using any integers, not just the positive ones, the counting numbers, but also the negative ones. So we consider something like 3 times negative 4. Now again, we can interpret this as simply saying 3 rows of negative 4. And that's exactly what this picture says right now. 1, 2, 3 rows of negative 4, or repeated addition by negative 4 plus negative 4 plus negative 4 equals negative 12. But one of the things we want to think through this time is, what if I wanted to say not just 3 times negative 4, but what if I wanted to do the same thing I did here where I flip the picture around and that flips the multiplication statement? 5 times 7 became 7 times 5. Can I let 3 times negative 4 be negative 4 times 3? And what kind of repeated addition statement would this end up being? Or what kind of picture would this end up being? If you watched the last video, you know that it is not simply the case right now that we simply rotate this rectangle. Because when we rotate this rectangle, we actually end up with a totally different multiplication statement altogether. I'm still counting here 4 rows, positive 4 rows, right? 4 rows. But this time the rows contain negative 3. So I definitely believe that 4 times negative 3 is going to give me the same result, negative 12, but I'm using totally different numbers now. 4 and negative 3 are not the same thing as positive 3 and negative 4. Clearly there's some kind of connection here, but this is not what we're looking for. These are not the droids that we're looking for. What we want to be able to do is not just turn this rectangle around and get a different multiplication statement. We want to find a reason to believe that commutativity is still going to apply here. That 3 times negative 4 can actually be stated as negative 4 times 3. But we want some kind of representation, using these same blocks, hopefully, of what that means. How are we going to represent not some positive number times a negative number? So you might notice that's what's happening every time that we start stacking up these rows. Because a row is a thing that we actually count, we would always represent it with a positive number. And we've already said that these rows should come first. And so we have some positive number as the number of rows that goes first. And then if we use the bad guys, the negative number is what would come second. But we want to flip that around. What are we going to do? We want to represent negative 4 times 3. We need negative 4 rows somehow. I'm going to show you that I think the best way to understand a negative row is to take away a row rather than to add it. But right now I have nothing, right? I have no rows of anything. So how am I supposed to take away a row from nothing? This is where I need good guy and bad guy to work together. Remember, they annihilate each other. One is positive 1, one is negative 1. Together they make 0. So when I'm looking at these two guys right here, I'm thinking that's actually nothing on the board. So I'm going to put a bunch of nothing on the board right now to represent negative 4 times 3. I need at least 4 rows of stuff to take away, but again, I want that stuff to be worth 0. So I'm going to put down a bunch of these pairs in an arrangement of 4 rows. Hopefully you can see, roughly speaking, we've got 1 row of 0, 2 row of 0, 3 row of 0, and 4 row of 0. Now, I said minus 4 rows was really going to mean take away 4 rows. But take away 4 rows of what? 4 rows of positive 3. And so I'm going to take away 1, 2, 3, 4 rows of positive 3. And what am I left with when I'm doing that? I have 12 bad guys now. I know this is equal to negative 12. I now have a reason to believe I can multiply a negative first by a positive and also end up with a negative product. So we have a sense of why we can multiply a negative by a positive and get a negative. And we already knew why we could multiply a positive by a negative. We know for sure things like 3 times negative 4, that is 3 groups of negative 4 or 3 rows of negative 4, clearly make something like negative 12. We have an idea now of why something like negative 4 times 3, its commuted analog, right? We just flipped the order, should also be negative 12, even if we think of it in terms of rows, because now we know, oh, minus 4 times 3 means take away 4 rows of positive 3, and using 0 pairs we're able to accomplish that. Does this also give us a reason to believe that a negative times a negative should make a positive? And unsurprisingly, the answer is yes. So consider that same set of 0 pairs. This time, let's say what we want to accomplish is negative 4 times negative 3. What would that be? We've said already that this initial minus 4 actually means take away 4 rows. And this negative 3 means take away 4 rows of negative 3. So I'm actually going to jot that down. Take away 4 rows of negative 3. So I'm going to take away 1, 2, 3, 4 rows of negative 3. And lo and behold, what do I have left? Positive 12. So it works, right? We have a sense now of why a negative times a negative would also be a positive. Something like positive 4 times positive 3 means we want 4 rows of positive 3, and of course that's going to make 12 by skip counting or by repeated addition. We now have a sense that minus 4 times minus 3 is going to work the same way. When we take away 4 rows of negative 3, it leaves us with positive 12. I think that's pretty cool. It's somewhat satisfying, I would say, but not super satisfying because we're still just taking multiplication back to repeated addition or something kind of like repeated subtraction. And that's okay, but we think multiplication is something more. We know that we should be able to do things like 1.5 times 3. Well, how do I add a 3 to itself 1.5 times? What is a half row going to end up looking like? And certainly, what about those weird numbers like pi? How am I supposed to add pi rows of something? You know, pi rows of 3 or something. How am I supposed to do that? So that's what the next video is for. This is as far as we're going to go today. We have a good reason to believe now. Positives times positives are positive. Negative times negatives are positive. Positive times a negative and a negative times a positive are all going to be negative. So we have a good sense of how to work out any kind of integer multiplication. But how are we going to extend this? How are we going to better understand rational multiplication or even irrational multiplication, those weird numbers like pi or the square root of 2. How are we going to get square root of 2 rows of something? Well, spoiler alert, we're not. We're not going to use rows anymore. We're going to use something more fundamental. I hope that was helpful to you. Make sure to let me know if you have any questions about that, and I will see you all next time.